And I would like to thank the organizers for inviting me and also for organizing this event. But I will talk about this joint work with János Nagy, and some part of it is also with István Tomon. So let me explain first the conjecture which was mentioned in the title. So the Alon-Jaeger-Tarsi conjecture states that if we have a field of size at least 4 and a non-singular matrix M, then it is always possible to find a vector which has no zero entries, such that its M image has no zero entries either. Since most of the talk will be devoted to this question, maybe I write a statement on the board. So the Alon-Jaeger-Tarsi conjecture states that if we have a field of size at least 4 and M is non-singular, then there is a vector x such that for every I, the coordinates of x are different from 0, and the coordinates of the image are also different from 0. This conjecture was first formulated by Jaeger in 81 in Hungary, actually, and it was also formulated by Alon-Jaeger-Tarsi when they were trying to generalize some properties of sparse graphs to more general matroids. So first, let me talk a little about the necessity of these restrictions on the size of the field and on the matrix. If the field is very small, then there is easy to find counterexamples. For instance, in case of the 2-element field, this 2 by 2 matrix is a counterexample. Here there is only one candidate for a vector which has no zero entries, the all-one vector, but in this case, the first entry of the image will be a 0. So for the 2-element field, the statement is false, and it's also false for the 3-element field. Here again, we can find the 2 by 2 counterexample. In this case, if we are looking for a vector which has no zero entries, then there are 4 candidates. Both entries can be either +1 or -1. If we choose the 2 entries of x to be the same, then the second entry of the image will be a 0. And if we choose the 2 entries of x to be the opposite of each other, 1 -1 and or -1 +1, then because of the first row, the first entry will be a 0. Another way to think about the conjecture and this counterexample is the following. In fact, the statement is that if we take 2 coordinate systems in f to the n, then we want to find a vector which has no zero entries in either of these 2 systems. Or if we would like to think about it as a covering problem, this counterexample over F3 is the following. To find the counterexample, we need to cover all the points of f to the n by 2n hyperplanes. The first n hyperplanes are coming from the equations when we have a 0 coordinate in the first basis, and the other n hyperplanes are coming from the conditions when we have a 0 according to the second coordinate system. And here already in dimension 2, it's quite easy to cover everything. We can take the first basis to be this one. With these 2 hyperplanes, we covered half of the non-zero vectors from the space. And for the second system, we can choose the first coordinate line to be this one, and the second one to be this one, which covers everything. So if the field is very small, then it's easy to counter examples. And it's also clear that some non-singularity condition is needed for the matrix M, since, for instance, if M could have a full 0 row, then it would be a counterexample. So the conditions are necessary. Then I continue with some easy observations. Here, the field can be either finite or infinite, but The interesting difficult case is the finite case. It's not difficult to see that for infinite fields, the conjecture holds. For instance, over the reals, if we collect those points that are bad, they have zero measure. And for other fields of infinite size, there is also an easy argument which works. So the interesting part of the conjecture is the case of finite fields. And already for these, by Alon-Jaeger-Tarsi in the 80s, a very interesting partial result was obtained. Namely, they could prove that the conjecture holds whenever the size of the field is a proper prime power. So it's not a prime, but a power of a prime. They use the polynomial method to get this result. And after the result, the case of prime fields remained open, where the prime needs to be at least 5. The questions related to several questions in the area. In case of some of these, there are some direct implications, but in most cases, it is just expected that some advance in case of one of the problems will probably lead to advances in the other problems. There are some conjectures about the permanent of matrices that are related to this. I mentioned one of these, the permanent conjecture of Kahn, which states that the permanent rank of the matrix MM, we take two copies of M next to each other, is n whenever M is a non-singular n by n matrix. Here the permanent rank is the size of the largest square submatrix with non-zero permanent. And the polynomial method of Alon-Jaeger-Tarsi actually implies that if this conjecture holds, then the Alon-Jaeger-Tarsi conjecture also holds. Another related question is the so-called additive basis conjecture of Jaeger, linear Payan, and Tarsi, which states the following. It claims that for if P is a prime, then there is a constant which might depend on the prime. The strong form of the conjecture would be that this constant might be equal to P itself, such that if you take the union of C1P many bases as a multiset, then it's always an additive basis that I define right now. So subset of Fp to the n is said to be an additive basis if each vector from the space can be expressed as a linear combination of the vectors from the multiset B, such that the coefficients are zeros and ones. In other words, a multiset is an additive basis if the collection of all subset sums, or to be more precise, sub-multiset sums, contain everything. A special case, if we take the copies of the same linear basis, in this case, it's clear that we need to take at least p-1 copies of it, and p-1 copies are enough. But in the general case, of course, the bases might be different from each other. So this conjecture is still open, and in 2007, Balázs Szegedi formulated a weakened version of it, which states that for every prime, there is a constant which might depend on the prime, such that if you take the union of C to P many bases, then every vector can be expressed as a linear combination of these vectors, where the coefficients can be any non-zero element of the field Fp. So here, it is not that important that the two values that we can use here are 0 and 1, and here 0 is the missing one. We should think about it in the way that here we can use just two coefficients, and here we could use all coefficients with the exception of just one. These problems in the area are also related to nowhere zero flows that are briefly mentioned. So that's a nowhere zero free flow conjecture states that every 4H connected graph has an over 0-3 flow. Here, in case of a graph, by a modulo K orientation, we mean an orientation of the edges such that the in and out degrees of every vertex is the same modulo K. And the constant C3 is defined to be the smallest constant such that if we do have C3K edge connectivity, then there is a modulo K orientation. With this notation, Tat's conjecture states that C3 of 3 is equal to 4. And Jaeger formulated a much stronger statement. His circular flow conjecture states that for K, the answer is 2K minus 2 whenever K is odd. Or, as a weaker version, just that such a constant exists. The existence of such a constant was proved by Thomassen. Lovász, Thomassen, Wu, and Zhang proved a quantitative bound on this quantity, which is larger than the conjectured 2K minus 2. Finally, Han, Li, Zhu, and Wang showed that the strong version is false if K is sufficiently large. And here the connection with the additive basis conjecture is that if the additive basis conjecture holds, then we have a quantitative correspondence between these constants. So these were some related problems. And as I have said, in some cases, there are some direct connections. In some other cases, just the nature of the problems are very similar to each other. And it's expected that similar tools may be required to make advances there. Although for a long time there was no progress in the Alon-Jaeger-Tarsi conjecture, Dufoss formulated a more general statement in this direction. In case of the Alon-Jaeger conjecture, we just want to avoid the zero coordinate, so just one value. But we might want to forbid more values to be used as coordinates. So let's say that the matrix is AB choosable if for any choice of A element sets xi and B element sets yj, it is always possible to find the vector x in the direct product of the x's such that its M image y is in the direct product of y's. In other words, we want to forbid more values for each coordinate of x and for each coordinate of the image of x, y. And these can be chosen independently for the different coordinates. In the case of fields of characteristic 2, Dufoss proved that every non-singular matrix is K plus 1, F minus K choosable. And in the setting of prime fields, he conjectured a similar statement that every non-singular matrix is K plus 2, P minus K choosable. It's not difficult to see that this is the strongest possible statement which has a chance to hold. And if you think about the balanced case, then it means that when the two values are equal, then it means that by K we can go roughly up to P over 2. So if this choosability conjecture of Dufoss holds in this form, then it means that for every coordinate of x and every coordinate of mx, we can forbid roughly half of the values from Fp to be used, and we can still find a suitable pair of vectors x and y. In case of the Alon-Jaeger-Tarsi conjecture, the statement is that every non-singular matrix is P minus 1 choosable. We just want to avoid the zero entry. A few more partial results from earlier times. Alon proved the observation that if M is chosen randomly, then the conjecture holds almost surely as n is tending to infinity. While you proved that the conjecture holds if n, the size of the matrix, is less than 2 to the p minus 2. So these two statements mean that if for some p there is a counterexample, then the smallest counterexample needs to be large. The size of the matrix is at least exponential in terms of p. But on the other hand, for large matrices, there can be only very few counterexamples. By these statements and also by some other considerations, heuristically, one can convince themselves that there is very little chance for the conjecture to be false. It can only happen if the field is too small, but those were the cases when the size is 2 and 3. But it's a different thing to actually prove something. So our results are the following. We could prove that the conjecture indeed holds if the prime is sufficiently large. And we prove it in this slightly more general choosability version when for every coordinate we can choose the forbidden value independently from each other. So xi should be different from some ci, and mxi should be different from some di. Of course, it's not a big surprise that the value 0 is not that important. We can forbid any value for any coordinate. And towards the choosability conjecture of De Vos, we made the following progress. If k is at most roughly log p over log p, then we could prove that every non-singular matrix is p minus k choosable. So instead of forbidding just one value for each coordinate, we can forbid log p over log p values. Once again, the strong form of the choosability conjecture would be that here, by k, we can go up to p over 2. So we have this log p over log p result right now. And in our proof, we use group ring identities. Now I just show a conjecture that we formulated and plays a crucial role in our proof. So let P be a prime which is larger than 3, and we have a non-singular matrix M over Fp. I denote the standard basis vectors by E1, En, and the rows of our matrix are A1 and An. And we take a certain group ring identity over the integers, but maybe first I would explain my notations. So I'm using the multiplicative notation for group rings, meaning that G is just a formal variable, and in the group ring we have such linear combinations where the coefficients are taken from a ring R. And we add these up in the natural way, and multiplication is also defined in the natural way. If you don't like this multiplicative notation, then instead of RV, GV, you should just think RV times V. But on my slides, I will have these multiplicative notations. So getting back to the conjecture, our conjecture states that a certain group ring identity over the integers follows from the same group ring identity, but now looked over Fp. Of course, here the reverse direction is clear. If we expand out the brackets and all coefficients vanish as integers, then they also vanish mod p. But we believe that from the condition that every coefficient vanishes mod p, it follows that they also vanish as integers. And what we proved is that for every prime, this conjecture implies that the Alon-Jaeger-Tarsi conjecture holds. And we could also prove that this conjecture holds if P is sufficiently large. Here, to be more precise, being sufficiently large means that P needs to be larger than 61 and be different from 79. So somehow 79 is an unlucky prime for our argument. Later I will show what is the reason behind this. But before getting to grouping identities, I would like to continue with some tools from additive combinatorics. In our proof, the main idea is to prove this conjecture for grouping identities, and for this we need several tools from additive combinatorics. And some of these questions might be interesting on their own right, so I would continue by explaining these. So now, for a few minutes, you can forget about grouping identities, and I will stick to additive combinatorics. So let's say that a non-empty subset of Fp is Sk type if for every element of the set we can find a 2k plus 1 term arithmetic progression where the middle element is A from this set. So we are looking for a set in which around every element we have a 2k plus 1 term arithmetic progression, and we would like this set to be small. The empty set should be excluded. SKP is defined to be the smallest possible size of such a set, such a non-empty set. Last year, here at this event, I talked about how to avoid arithmetic progressions in FP to the n. Here, I will try to include arithmetic progression in FP. So once again, for every element, there should be a 2k plus 1 term arithmetic progression whose middle element is from the chosen element from the set. And the related notion is being nk type. Here we still have the previous requirement, but we also require something if an element is not in the set A. In this case, the existence of such a k plus 1 term arithmetic progression is required, where the first element is A, which is out of our set, but all the other elements are contained in this set. So here the requirement is somewhat stronger. And here again, we will need sets of small size satisfying this condition. In case of the Alon-Jaeger-Tarsi conjecture, what we need in our proof is that the size S1p should be strictly less than the square root of p minus 1. If k is equal to 1, then the two conditions are the same. So here the requirement is that if something is contained in this set, then it should be the middle element of a 3-term arithmetic progression. And if something is not contained in this set, then there should be a 2-term arithmetic progression where the other element is contained in this set, but this holds. So in case of k equals 1, which is the setting of the Alon-Jaeger-Tarsi conjecture, there is no difference between the two quantities. And it turns out that in this case, such sets can be chosen to be very small. In fact, it holds for every p that the quantity is at most 2 log 2p. And the quantity was also studied before. And in fact, the right growth rate is 1 plus little o of 1 times log 2p. But if p is very small, then this, of course, might be weaker than what we need. So for the small primes, we had to use some heuristics to find sufficiently good constructions and also use some computer help. And it turns out that these are exactly those primes where this bound holds, which at the moment is crucial for our argument to work. And this might already suggest that the problem is 79 is that it's just slightly less than a perfect square. So we needed a set satisfying this condition of one larger size, and it doesn't work out. If we go down to 73, then the size of the field is getting smaller, and there is a suitable construction. For 79, that there isn't. In case of the choosability version, what we could prove is much weaker. If P is at least that large, then we gave such a bound with the help of an explicit construction. And I think this is one of the points where there is space for some improvements. And understanding the size of SKP seems to be an interesting question on their own right. Let me briefly explain why the situation is much more difficult if K is at least 2. So what we need for the Alon-Jaeger-Tarsi conjecture is to find such an arithmetic progression for every element. And we can just add elements by one by one. So we start with 3 elements that are in arithmetic progression. The middle element is fine. This is not a middle element of the arithmetic progression. But if I reflect an already added element to this element, for instance, I reflect that one, then it will also be fine. So by adding one new element, one element will be fine. What I need to achieve during this process is that, at one point, I have to do it in such a way that by adding one new element, another element, which was not fine, will be made fine. And if we add elements this way one by one, by these reflections, then the diameter of the set can be made twice as large as in the previous step. We are in FP, so we can go around. There is also some flexibility, how to choose the element that we reflect. And in log 2p steps, we can succeed. This cannot be done if we need a 5-element arithmetic progression or an element, since here, if one element is not yet fine, then this will need to add 3 more elements to make the condition hold. We gave a recursive explicit construction. It provides such a bound, which is enough to prove the choosability version that we have, but we do not know what is the right answer for SKP. And for NKP, again, if P is sufficiently large, then we have such a bound, which is proved just by random construction in an easy way. And the square root of P minus 1 is coming from the following easy lemma. If we take 2 bases, E1, En, F1, Fn, and we have some subsets of non-zero elements of Fp, then if we have this restriction on the product of the sizes of these subsets, then it is always possible to choose non-zero coefficients lambda I, such that whenever we take a linear combination of the EI vectors, where the coefficients are taken from the UI sets, we get a vector which is different from any vector, which is a linear combination of the Fi vectors, where the coefficients are some dilated versions of coefficients taken from the VI sets. Here again, this lemma can be easily shown with the help of random choice, and the proof works if we have this bound. In our context, the sets will need to be SI type and NI type, so that's why we need to require that S1P is less than the root of P minus 1, which is not the case if P is very, very small. less than 61. And in the choosability version, the product of the two quantities should be less than p minus 1. So if one can prove that this bound holds from a smaller threshold, then our results are getting improved just by improving on this additive combinatorial part. So now I switch back to grouping identities. It is important to understand the statement of the conjecture, in fact, better. And I will show some equivalent conditions for the statement that the conjecture is false. So the first property just states that for the prime P, the conjecture of Alon-Jaeger-Tarsi fails to hold. There is no vector which has no zero entries such a way that its M which has no zero entries either. Then at some point, it seems quite natural to use a polynomial technique because it is perfectly clear that this is the same as saying that if you take the product of the 2n coordinates, which is a polynomial of degree 2n, then it vanishes everywhere. So to prove that the conjecture holds, its office is to prove that it is not possible that this specific 2n degree polynomial vanishes everywhere. However, it turns out that it is not useful enough in this setting, or at least somehow there is no argument which can get the result with the help of just this polynomial. So here it turns out to be much more useful to work with grouping identities. It is also equivalent with these two conditions about the falseness of the conjecture, that this grouping element, where the element is looked over the integers, is 0. So the coefficients are zeros. Then I show two more properties that are not exactly equivalent, but they follow from these properties. And so far these three are equivalent to each other. And the next property is that this group ring element, which is formally the same, but now looked over Fp, is also 0 there. It is a clear implication of the third property because if all the coefficients are zeros as integers, then they are also 0 mod p. And although in this talk it will not be important, I show a fifth condition, which states that if we take this polynomial, which also appeared in the second property, and we reduce it, then the degree of the reduced version will be less than 2n. What I mean by reducing, this is the product of 2n linear homogeneous polynomials. And it might happen that some of the individual degrees will be larger than p. But if an exponent is larger than p, then we can decrease it by p minus 1. We do it for all the variables, and in this property states that the degree of this reduced version of this 2n degree polynomial will be less than 2n. So once again, this is the connection among the 5 properties. And what we prove is the falseness of the fourth property. So we prove that whenever S1p is less than the square root of p minus 1, then it is not possible that this grouping element is 0. And according to the previous connection between the properties, this implies that the conjecture holds, because from the falseness of the conjecture, property P4 would follow. So for proving the conjecture for a certain prime, its office is to prove this statement. In the choosability version, The difference is that we also need this nk quantity here. So here the product of those two should be less than p minus 1. And the grouping element, in the grouping element, we have these exponents k. I showed some part of the proof, which is by induction on n. So we need these connections between different properties being similar to the falseness of the conjecture and the additive combinatorial tools to push through an inductive proof. The base case is very easy. Here we have this product, and it's clear that it is not possible that every coefficient is 0. So let's continue with the induction step. For the sake of contradiction, we assume that the statement is false. So this grouping element is 0. And we would like to reach a contradiction. First, we use a lemma that I do not prove. And this additive combinatorial machinery that I mentioned is used of this lemma. The lemma states that if this 2n factor product is 0, then it is also 0 if we leave out one of the one suitably chosen factor. So let's believe this lemma for now, and I will prove the statement with the help of this lemma. So the assumption was that this is 0, and according to the lemma, we can choose an index j such that this 2n minus 1 factor product is already 0. Then the proof of this theorem is obtained in the following way. So for this j, we can choose an index L such that MJL, which is the matrix obtained by deleting the j's row and s column, is non-singular. The AI vectors are the row vectors of the matrix M. And now we write in each of them the component in the direction of the basis vector EL separately. So in AI prime, the coefficient of EL is 0. This way, these AI prime vectors lie in a one less dimensional subspace because the EL coordinates are equal to 0 in case of these. If I is an index different from J, then let's write the grouping element 1 minus GAI as the sum of 1 minus GAI prime plus some multiple of 1 minus GEL, which can be done since the difference of AI and AI prime is some coefficient times EL. Now, according to the lemma, we know that this 2n minus 1 factor product is equal to 0. And in the second product, we use this expression in place of 1 minus GAI. And we can think of B as a linear combination of elements of the form 1 minus GEL to some exponent. We expand out the brackets, and in each product, we get a certain number of copies of 1 minus GEL. What can be their number? We will certainly get at least one of them, because here in the first product, 1 minus GEL must be chosen. And if R would be at least P, then this power is 0. So the P's power is also already 0. So it's sufficient to go up to P minus 1. These are linearly independent from each other. And we know that B is equal to 0, meaning that here every coefficient needs to be 0. Specifically, B1 also needs to be 0. But what is B1? In case of B1, when we expand out the brackets, we choose only one copy of 1 minus GEL, which is here, the S product from the first else factor from the first product. And we don't need more. So from the second product, in all the cases, we need to choose the first summand. So B1 is equal to the product of D1 minus GEI factors from the first product and the product of those from the second product. But the condition that this 2n minus 2 factor product is equal to 0 is the same as the statement that property P4 fails to hold for the matrix MJL, which has size only n minus 1. And it was an inductive proof, so this is a contradiction. In the remaining time, I would talk about mention some applications of this technique. So the first result is a strengthening of the statement. So the Alon-Jaeger-Tarsi conjecture is about 2 bases, but we can take more. For any k, there is some threshold such that if a prime is larger than this threshold, then if we take k non-singular matrices over Fp, then there is a vector such that none of the MIX images have 0 coordinates. In case of the Alon-Jaeger-Tarsi conjecture, we have just 2 matrices. So K is 2. We have the identity matrix and the non-singular matrix M. In other words, we have just 2 coordinate systems, but we can have any. If the field is too small, then there may be counterexamples, and there are counterexamples. But for every k, after some point onwards, the statement holds. And from our original proof, it was not clear that this can be proven because we played with some duality, but the stronger form also holds. We made a little step towards the additive basis conjecture, which is stating that by taking CP many, the union of CP many bases, everything is a 0-1 linear combination. Here we could prove something which is much weaker than the additive basis conjecture, but implies the weaker version where we can use any non-zero coordinate for coefficients. In fact, we proved 2 statements, both of which imply the weak version. In case of the first statement, we proved that it is possible to find a size, find a subset of Fp of size 2 log p, such that if we take the union of p bases, then every vector is a linear combination of vectors taken from the multiset, which is this union, such that the coefficients are taken from this set of size 2 log p. And what we need about this set is to be of S1 type. So to have a straight arithmetic progression around each of its elements. And the second statement is that we are indeed allowed to use any non-zero values for coordinates. Then it suffices to take the union of 3 bases. So here in the weak version, the statement was that coefficient set of size p minus 1 is fine. The strong version is that coefficient set of size 2 is also fine. So we could prove it 2 log p, but just for a specific coefficient set. So the additive basis conjecture is still open. And as I have already mentioned that it's clear that the question is related to coverings by hyperplanes. So to conclude my talk, I would like to mention an application towards this direction. It's an old result of Tompkinson that if A is a group and we have an irredundant coset cover of this group, then the index of the intersection of these subgroups in A is big O E to the big O of K log K. So by an irredundant cover, I mean a cover, coset cover, where we cannot leave out any set from this cover. And this bound is actually tight. In fact, this is, to be more precise, this index is at most K factorial. And there is an example for a group where it's exactly K factorial. So in the general setting, this result cannot be improved. But Piper asked whether for abelian groups something stronger can hold. And Szegedy asked quantitatively whether the bound, the exponent can be improved to big O of K. So whether one can get rid of log K in case of abelian groups. We could not prove this statement, but we could strengthen on that result by showing that this index is at most E to the big O of K log K. And here, if the conjectured E to the big O of K bound is correct, then it's tight, which can be seen by an easy construction like this. So during the talk, I mentioned some tools that may be improved. So I end my talk by mentioning these again. So we could not determine very precisely the right growth rate of the quantities SKP and NKP. So these were the quantities where around each element of the set, we would like to see a 2K plus 1 term arithmetic progression. In case of SK and in case of NK, there was another condition that if something is not contained in this set, then we need a K plus 1 term arithmetic progression such that all the other elements of this arithmetic progression are contained in our set. So determining the growth rate of these two quantities would be helpful. And for the current argument that we have, what we need is that we have the choosability version whenever the product of NK and SK is less than P minus 1. Another question is proving this conjecture. We prove this conjecture if P is larger than 61, but different from 79. We also proved that for the remaining small primes, if for such a prime this conjecture holds, then this implies the Alon-Jaeger-Tarsi conjecture. But for small primes, so primes below 61, we do not have a proof of this statement. These are the two papers I was talking about, and I would like to thank you for your attention.